Thank you for coming. This afternoon we have for you Vadim Zavalishin's The Art of VA Filter Design and Different Kind of Digital Filter Theory. Vadim's worked in the audio industry for about 2 decades. As a Native Instruments employee, he's been mainly responsible for the development of Reactor Core graphical audio programming language. He also does DSP research, the most known of his works being The Art of VA Filter Design. Let's hear it for Vadim.
Good afternoon. Thanks for your interest. So many people here. Thanks for Florian for kindly lending me his laptop for this presentation. So the talk is basically a presentation of the book, The Art of Virtual Analog Filter Design. The book itself has been out for over 6 years, as many of you probably know. But this summer, it has received a major update to revision 2, and this is the occasion for this presentation. And there was a minor update quite recently, as usually freely available as a PDF download from Native Instruments website, mirrored from Disco DSP. But it's best to find it through KVR Audio web forum, because then you can be sure you get the latest revision and not the ones which search engines throw at you. The talk will be split in 2 parts. So the first part will be about the motivation and the structure of the book. And the second part will be about some highlights of the second revision. Let's go. The motivation behind the book is rather bold. It's replacing standard DSP texts as introductory text into filter theory, digital filter theory, for the purposes of DSP industry, of music DSP industry. And replacing, I definitely don't mean discarding. It would be a bit too bold goal, of course, discarding work of hundreds, thousands of people, who knows. But just providing a different entry point from a different angle, which is much more suitable, at least in my opinion. Your mileage may vary, let's see, for the music DSP industry needs. The problems with standard text or with standard DSP, in my opinion, come not because they do things bad, but because they're having a different focus. In standard DSP, a filter is basically just a way to cut out a range of frequencies from the signal, and that's it. And this defines the priority points, which you can see on the left side of the slide. In comparison, music DSP, our priority points are completely different. We're interested in musically relevant qualities, and those are like filter roll-off, filter cutoff, resonance. We want nonlinear elements. We want modulation going into the audio rate. And this actually results in the fact that solutions found in one branch, like in standard DSP, are not the best solution, not too well working for our purposes. And I'm about to demonstrate it. So this slide demonstrates for me the essence of classical DSP filters. This is the difference equation and the structure implementing it, the famous direct form. And I'm having here a reactor setup illustrating the problems with this kind of filters. So I'm having here a direct form 1 resonating low-pass filter. Let's imagine I'm a DSP newbie, and I read the classical DSP text, and I found transfer function for this resonating filter, and I build it. And let's listen to what is my result. So it's a low-pass filter, right? Sounds like one. It can resonate. Sounds like a resonating low pass. So far, so good. But now let's start modulating this filter. So I'm going to be modulating it by an LF4. Coefficient update is at full rate, so it's as good as it gets. And now I'm going to increase the rate. And sometimes we're getting this kind of weird low rumble. And with direct form 2, it's going to get even funnier now. So please watch out now. The volume is going to quickly raise, probably, because the artifacts there are much stronger. This is direct form 2 instead of direct form 1, another classical structure. And if I increase the rate further, at some point, bang, the filter just explodes. This is as nice as it's working. In comparison, an analog filter in a similar setting would sound like this. So the modulation artifacts would be kind of more smooth, and there would be no explosion whatsoever. So this is probably the major problem. Another problem with direct forms, so here I'm having direct form to high-pass filter, and it kind of sounds okay, but at some coefficient settings, not necessarily even as extreme as this, just for the illustration, I'm going extreme, we're having very large quantization noise. This shouldn't happen, like what we should get is this. So 32-bit floating point, not sufficient to get the computations done. We need 64-bit. So these are the kinds of problems which we're getting with the solution. Back to the analog filter, which presumably handles cutoff modulation correctly. When I'm saying analog filter, I don't necessarily mean electronic circuit. I would think of analog filters in terms of abstract block diagrams. So the difference is block diagrams are continuous in time. So the time is continuous, not discrete. And this means that instead of unit delays like we had on this slide, we're going to have integrators. And this slide, by the way, shows the famous state variable filter in its analog form. And it just so happens mathematically, that's exactly the usage of the integrators which is responsible for nice behavior under modulation. So there's a simple mathematical transformation whose basic result is, given our cutoff is uniformly positive, cutoff modulation can be equivalently seen as a warping of the time axis. So the filter is actually even not being modulated at all, and stability of filters is well-known research subject. If the filter is stable and not modulated, it stays stable. So that's kind of an explanation why integrators work so nicely. And for that reason, until approximately a decade ago, I would say modulation-based filters were integrator-based filters were heavily used in music DSP, but with integration schemes based on Euler and Euler-like methods. And this method solved the cutoff modulation problem, but you get quite a number of extra artifacts in response, especially close to Nyquist, and those are not easily amended and even can't be fully amended in comparison to bilinear transformed filters which we got in classical theory. So at least something classical theory got right. A much less known approach, for whatever reason much less known, trapezoidal integration, was almost arcane knowledge, for whatever reason, although known for decades, is working much better. It's actually giving you exactly the same frequency responses as classical DSP filters with bilinear transform. And somewhere I even read a statement that bilinear transform is the same as trapezoidal integration. I hope that I read it taken out of the content, because I think this statement by itself is plain wrong. I'm not going to go into the details, but in the beginning, we had heard 3 different filters sounding very differently. All 3 filters had exactly bilinear transformed frequency response, but only one of them was actually trapezoidal integrated, and only that one worked nicely. So there is definitely no equality sign between those. Trapezoidal integration implies bilinear transform, but not vice versa. Probably because trapezoidal integration wasn't that widely known, it was rediscovered about 10 years ago in the form of topology-preserving transform. So if trapezoidal integration is working symbolically on differential equations, topology-preserving transform starts from block diagrams, and there we replace all integrators in the diagrams with their discrete time forms, bilinear transformed integrators. So you can pick any bilinear transform integrator. Would work equally well, mostly, but other things being equal, I think it's usually best to use transpose direct form 2 integrator, which is shown on this slide. And here I would like to give credit to René Jeschke, who suggested usage of this specific integrator in the context of topology-preserving transform. After the integrator replacement, we are going to get zero delay feedback loops in our block diagram. And this is another weird thing about music DSP industry, because for whatever reason, even though, again, zero feedback resolution has been known for decades, it has been systematically avoided. I don't know why, but it has been. And people would say, we can't have zero delay feedback. We need to resolve it by inserting a unit delay to break it, which obviously kills the frequency response. So topology-preserving transform says you should properly resolve zero delay feedback. And then we're getting pretty much the same results as from trapezoidal integration, so 2 methods are almost equivalent. And the filters obtained by either method are currently famous under the name ZDF filters. This is what the book is going to be based on. It's based on topology-preserving transform as a way to construct DF filters. Now let's get closer to the book subject. Let's talk about preliminaries. In a classical text, before we get to the filters, we learn about lots of theoretical stuff, again, like on the left of this slide. And maybe partially because many of these books would be dealing with more than just filters, but also partially because of the way the filters are introduced in classical DSP. So the book, The Art of VA Filter Design, has a very small set of preliminaries. For one sampling theorem, you basically just need an amateur level of understanding of sampling theorem statement, more or less. So it even doesn't talk about it. And then we need a small bit from Fourier theory, just a basic result that any signal can be represented as a sum of sinusoidal partials of different frequencies. That's just for our understanding, to understand that the filter simply treats each of these partials differently. That's what filtering is. And there's a very short introductory chapter in the book which just restates this in mathematical terms. And that's as much as you need to have of the preparatory material. And now we get to talk about the core part of the book. So again, I'm now running comparison of the book's table of contents against a table of contents of an imaginary classical text, something how I would picture a typical classical text. Again, on the left, you see kind of a bunch of mostly theoretical subjects. So in comparison, the Art of VA Filter Design book organizes the material based on filter type. And we study exactly the filter types which are commonly and widely used in music DSP. Those are kind of, you can say they're virtual analog filters, but even in a synthesizer which doesn't claim itself to be explicitly virtual analog, like wavetable synthesizer, like filters of this kind would be like very nicely used. So the book goes through the types of filters commonly used in musical DSP. And this is starting with one-pole filter, basically RC filter, state variable filter, very famously used, and a class of ladder filters or resonating feedback, which is like Moog ladder filter, diode ladder filter. Silent K filter can be seen as a ladder filter. And phasers and flangers are actually ladder filters. So it's a very common filter type, and I think also it's probably most intuitive resonating filter type. Because in comparison, state variable filter has two feedback paths, and one path is fixed, one has variable gain, and the more gain you have, the less resonance you have. Like this, absolutely counterintuitive. And with ladder filters, the more gain in the feedback you have, there's just one path. The more gain is there, the more resonance you have. So it's a very intuitive picture. These filters are studied in the form of abstract analog block diagrams, so even not in discrete time forms. And there is just one chapter coming exactly after the one-pole filters, after we study our very first filter, which teaches you the topology-preserving transform. Basically, this is how you convert these diagrams to digital form. And the idea is that this conversion is basically a routine process. So that what the book is trying to propose as a way of thinking in filter design is that you think in terms of analog block diagrams, because things are simpler there, the math is simpler there, in my opinion. So the idea is that the DSP engineer would think in terms of analog block diagrams, and then there is just this routine which you, at the end, simply apply almost implicitly and convert your filter to something which can be implemented digitally. This is essentially the idea of the book. Then I didn't mention this other chapter here, nonlinearities. Of course, another important topic for music DSP, how to build nonlinear filters, where again, we're covering standard ways of using saturators and anti-saturators to make nonlinear filter types. So as you may notice, here we just studied some standard filter structures. But it's actually not a goal of the book to simply teach you how to do a Moog filter in digital form, which is kind of nicely modulatable and what have you. The purpose of the book would be, as I said, to teach thinking in terms of analog block diagrams. So it's kind of contradicting would be DSP engineers, but the idea is to say you should think in analog terms simply because it's easier and much more efficient. And then you're ending up with filters which are efficiently usable in music DSP context. So this is the idea, to introduce this very different paradigm from classical DSP. Besides just studying filter types, of course, there are also these theoretical concepts, similar to the ones which you see on the left side of the slide, but just similar, different set of theoretical concepts, which might be more appropriate for, again, analog filter design theory. And here I would actually like to go into a bit more detail into the second bullet point, which is the transfer function algebra. So the book is introducing the transfer functions starting from block diagrams. First, you learn the transfer functions of individual elements of the analog block diagrams, which is very easy, very intuitive. And then you're just combining them algebraically, which is also like very simple algebraic process, and you're ending up with transfer function of a filter, of your filter structure. In comparison, I think usually transfer functions of digital filters are introduced as Z-transforms of filters' impulse response. And that, in my opinion, is also very counterintuitive because, I mean, unless we're doing FIR filters, which we're currently not, so it's a very special filter class, the filters, digital filters do not work by convolution with impulse response. The filters work by numerically solving the difference equation. But impulse response is a mathematical concept. It's very powerful, very elegant, I totally agree, but it has little to do with intuitive understanding of how the filter works. So as far as intuitive understanding goes, I think this transfer function algebra is sufficient. It's not completely rigorous. There are a couple of subtle points which are like open certain questions. And for more picky minds, there's also kind of parts in the book where the transfer function is explicitly derived from differential and difference equations. It's a bit more math heavy, but it's a more proper derivation. And again, in my opinion, this is an intuitive derivation because this is corresponding to exactly how the filters work. So just a small highlight of these theoretical elements. Oh, I'm even a bit ahead of time. Maybe I was rushing the talk a bit. But nevertheless, so I would say that concludes the first part. I hope I gave you a picture of why the book is different from typical texts, and maybe at least try to convince those who didn't read it that they might want to check it out and to see if this different angle is indeed working better for the purposes of music DSP industry. The judgment is up to you. So for now, let's get to the more fun part, although it will start a bit heavier, but I hope it will be still fun. Highlights of the second revision of the book. A large part of second revision material is basically describing the results of research, which I did at the time of the writing or shortly before, and looks highly theoretical. However, this research was made with practical questions in mind. If you just glance through the book, this might not be obvious, so I would like to highlight these practical outcomes of this heavy theoretical part. For example, I would like to start with a dome filter. So this is essentially kind of a result of almost 200 pages of heavy theory, not just for the dome filter, but it was the main motivation for me to include these pages in there. Dome filter, also known as Hilbert transformer phase splitter, is most famously used in frequency shifter effects. And it's a basis of frequency shifter effect. And essentially, it's two parallel chains of one-pole all-pass filters. And they need to be tuned to specifically chosen cutoffs for the filter to work correctly as a phase splitter. There is some set of pre-computed coefficients floating around since years on the internet. I think one and the same set mostly. I'm not sure, but I somehow think it was derived from analog diagram, basically from the circuit diagram of analog frequency shifter that Harald Bode built for Robert Moog's company. At least that's what I think. But if you want to build a different set of coefficients, if you want like to have a filter of higher order with more precision, different bandwidth, what have you, it seems it's almost impossible, or basically it's impossible to find information or at least complete information on the internet how to do it. There seems to be kind of hidden knowledge. Maybe it's available in some texts, probably, but Like lots of people ask, okay, how do I compute coefficients of dome filter? And almost nobody knows the answer. And I took the challenge of reinventing the wheel and finding the answer. There was already one in the first revision, but then I thought the formula is too bulky. It's like rather large and doesn't look elegant at all. And I thought there must be a simpler answer. And in revision 2, I managed to find this answer. In order to obtain it, I had to dive into theory of Jacobian elliptic functions. And again, starting from some public, easily publicly available results on the internet, I had to rederive further knowledge. And at the top of this slide, this is the key formula, which I obtained. It connects two different Jacobian elliptic functions via a rotation of Riemann sphere. At least it sounds very elegant. I don't know how many would really understand what it means, because then you really need to know the subject, of course. But I hope it at least sounds cool. Anyway, using this formula, I managed to obtain the answer. So this second formula, looking very simple, it's the answer for the tuning. It gives you the positions of the poles and zeros of the one-pole all passes. So essentially, they're cutoffs. And it might look daunting, but this is a standard function, standard Jacobian elliptic function available in very many standard mathematical libraries. So don't worry, it can be easily computed with a library. Also, the book explains how to compute it. But the formula itself looks very short, very simple. These are just the tunings of the one-poles. And to make it even less daunting, I am putting here its limiting form. When elliptic modulus is approaching 0, we go from elliptic filter into Butterworth filter. And then instead of this SC Jacobian elliptic functions, we're just having a tangent. So you can get Butterworth dome filter, which has a bit smaller bandwidth, so better do elliptic. So that was just a show off. At least now anybody should be able to build their own frequency shifters easily. Another small highlight, so far I'm going over small highlights, is generalized Linkwitz-Riley crossovers. Here, I don't know, it sounds for me, frankly speaking, as this should be known before, but at least this is not widely known. So maybe I'm again reinventing the wheel here. It started with a discussion on KVR audio, where I have to credit Max Mikhailov for giving some key piece of information triggering this research. And that was, he said that you can build Linkwitz-Riley crossovers not only based on Butterworth filters. I mean, if you know what Linkwitz-Riley crossovers are, like you would immediately think, okay, Butterworth filter. And he gave an example of using a naive one-pole low-pass as a basis for the Linkwitz-Riley crossover instead. And this naive low-pass is not exactly low-pass, it's more like a high-shelling filter. And he explained how to build a Linkwitz-Riley crossover out of this filter. It's a bit more involved, but basically still simple. And then naturally we ask ourselves a question, or which other filter types can be used? Because apparently it's not only Butterworth. And again, I took a challenge of researching this subject and found the answer, which is basically given by this formula. And this formula means you can take any filter. Well, probably you should take a low-pass filter, so you want your other band to make a high-pass. But in principle, any filter would satisfy, would allow you to build a crossover satisfying equation that they both add to an all-pass and they both have identical phase responses. So basically, you substitute your favorite filter instead of this fraction here, transfer function, and then the rest of the equation is uniquely defined, and basically you're getting your crossover. Again, I'm not going to get into the details of this because it's too much for this talk. But as a practical result, just to try out this formula, I have built an elliptic Linkwitz-Riley crossover. So there, the thing is that you use elliptic modules to control the trade-off between the leakage and the stop bands. So like the suppression is not just decaying, like with Butterworth, you're getting some ripples. You get leakage in the stop band, also in the pass band, but it's less noticeable. But then at the same time, your crossover transient region gets steeper. If we have some extra time at the end of the talk, I don't know, then maybe I can demonstrate it, not sonically, but just on the responses. For now, we'll skip further details. So that was the second practical result in elliptic Linkwitz-Riley crossover. And now I'm coming to the biggest section of the second part of the talk, which I hope will be most fun. Again, I don't know if it's old news. I am not aware of these ideas. So I invented kind of new terms, second kind Butterworth filters, Butterworth transformation, which the book describes. And then again, it looks highly theoretical, but I think you get lots of good practical results from this thing. And why I would like to talk about this in more detail is because the book just throws the Butterworth transformation out at you first, and then derives first kind and second kind Butterworth filters from this transformation. However, this is not how I came to the idea, and I thought it would be interesting to illustrate or to tell a story how this idea was developed and what it ended up with. So it started with a very standard DSP newbie question, which was like once again asked on KVR audio, how do I build a resonating low-pass filter of an order higher than 2? Because for the second order, there is just more or less one definite answer. You don't have many options there. It's just one way to build a resonating low-pass filter. For higher orders, you have lots of options. For fourth order, people could suggest, OK, use Moog ladder, but then Moog ladder looks very different from second pole resonating filter. And neither looks as a generalization of the other, and Moog ladder doesn't generalize nicely to higher orders either, so not an answer. Another attempt, let's just stack several identical two-pole sections together, why not, right? Unfortunately, you get a really wide resonance peak in the result, and it kind of sounds, I would say, like usually horrible. And when this question was asked again, this triggered for me, again, another attempt to find a solution, and ultimately, I think there were some failed attempts. I came up to this idea. I started with a classical Butterworth filter, which I'm now referring to as first kind Butterworth filter. So this is this design equation. If you know what Butterworth filter is, you should recognize this formula. And I decided to add an extra term to its denominator. The thing is that this extra term turns the denominator into a quadratic polynomial in terms of omega to nth power, like you can see here. So in terms of omega to nth power, it's just a parabola. And there is this minimum of a parabola. And then if you look at the graph of the denominator, then first it was just growing like this indefinitely. And now it gets this minimum first here and then grows. And after reciprocation, this minimum turns into a resonance peak. This was the main idea. Worked out immediately, with the remark that it worked out only for even n. For odd n, you don't get conjugate poles, so these filters do not exist. But for even n, worked out of the box, and I kind of found an answer to the original question. And that could have been it, but then I made another observation. By rewriting the denominator in a slightly different way, like this, I noticed that it's basically identical, or almost identical, to the denominator of the two-pole low-pass filter written in the same form. So basically squared magnitude response denominator. So the difference is here I'm having omega to nth power, here I'm having omega squared. And this here is not a difference, it's just how you define control parameters, it doesn't matter. So what I found out is that by this substitution, replacing omega squared with omega to nth power, I turn a two-pole low-pass filter, resonating low-pass filter, into a higher order resonating low-pass filter, which, oh, I forgot to mention, but I guess you already found it from the slide. So this filter I called original Butterworth filters, like classical Butterworth filters, first kind Butterworth filters. And the ones with resonance, I refer to as second kind Butterworth filters. So now there's this first and second kind. So back to this slide. This substitution turns a resonating two-pole low-pass filter into a higher order resonating filter. But then n must be even, which means I can redefine n and say I write 2n instead, where n can be odd or even, like this instead. And then the substitution just replaces omega with omega to nth power. And the next observation is that the very same substitution turns one-pole low-pass filter into first-kind Butterworth filter. So I'm having this beautiful substitution here, turning one and two-pole low-pass filters into first and second-kind Butterworth filters. Furthermore, so far we were dealing only with denominators, kind of acting on filter poles, transforming them. But I could do the same things on numerators on the same form, which means I can also transform zeros of the filters in the same way. And this means I could apply this transformation to any first or second order filter. And this also means I can apply this transformation to transfer function of any order, because I can simply factor it into first and second order sections and transform each of them in turn. So I'm now having this transformation, which I call Butterworth transformation, which can be applied to any filter. But what does it do? If we think that amplitude responses of filters, especially analog filters, are usually plotted in logarithmic frequency scale, then we should ask ourselves, how does this transformation look in logarithmic frequency scale? And there, raising to nth power means just multiplication by n. So essentially, we're just shrinking the amplitude response n times. As you can see on this slide, so white line before shrinking, sine line after shrinking, for example, from second order to fourth order. This is the effect of the transformation, which I'm now going to demonstrate a bit how these filters sound. So I will start with the second order filter. And now transformation with n equal to 2. So we get fourth order resonating filter. And the resonance gets thinner. Sixth order gets even thinner. Eighth order gets even thinner. And some people to whom I showed it said that it sounds kind of less musical because the resonance is kind of sounding too thin. I would partially agree to that, partially because, yes, to me it also sounds maybe a bit more musical immediately, but then I think it might be a cultural thing. It's because the resonance which we're using to are coming out of second order filters, and fourth order filters like Moog ladder, and Moog ladder also has a wide resonance peak. So here I'm having the Moog ladder in comparison. So this is the Moog ladder, this is second order. You can see and hear that the resonance has similar width and similar power. And this is fourth order Butterworth in comparison. So maybe the thing is that we're just not used to it. Don't know. At any rate, I think this filter already can be used musically in certain scenarios. As a way to compensate maybe a bit for this lost resonance power, I was also motivated to build a nonlinear version of this filter. And now I have a problem, because Butterworth transformation works with transfer functions. It just gives me a transfer function, doesn't tell me anything about topology. As long as this filter is linear, it doesn't matter much which topology I use, as long as I'm using nice topology integrator-based. They would all sound more or less the same. With nonlinear filters, topology would have much more impact on the sound, obviously. So what would be the obvious topological choice for a filter defined by the transfer function? You normally factor it into second order sections and stack them together. This is what I did for the linear case, actually, stacking two second order sections together. This is what we have heard. But if I do the same in nonlinear case, it would be maybe not so nice, because even if these two sections are nonlinear, then each has its own nonlinearity, and these nonlinearities are kind of independent. And usually in nonlinear filters, we have nonlinearity as a part of global feedback. It should affect the entire filter, so it kind of feels wrong. This is a solution which I came up with. The way how I arrived at it, I started with transposed generalized state variable filter, also known as observable canonical form. And then, keeping in mind that state variable filter doesn't easily accommodate nonlinearities, I replaced integrators with one-pole low-pass filters there. However, then looking at the structure, I realized I could have arrived at the structure in two other ways. I could just have started with a ladder filter, would be just have global feedback here, and add 3 more feedback paths here. Or I could have started with a silent key filter. It would be just this part, and then added 2 more sections on the left. So either of the 3 ways, at least, you end up with this structure. And I'm now going to show to you how it sounds. So now I'm going to drive this thing really. It's already driven forward, but maximum resonance. And in comparison, this is how silent key sounds. It's quite close to this, right? So what I have built is probably a four-pole silent key filter. And in comparison, a ladder filter with exactly the same nonlinearity would sound quite different. So we're having a four-pole filter with kind of different sound. So that's the practical application of Butterworth transformation. Not the last one which I'm going to demonstrate. I want to show you another one, which I think is also pretty cool. I'm not going to get into details how this is done. Again, you can read the book. But this is an 8-pole shelving filter, which currently, no sound this time, but I'm having an amplitude response plot. Let's concentrate on the visuals, which currently has an amplitude response of a 1-pole shelving filter. And I can turn this knob to smoothly morph the steepness of this response from 1 pole going through 2-pole, through 4-pole, going to 8-pole without any artifacts, so completely smooth. I can't go beyond 8-pole because my filter is 8-pole, so it's 8-pole Butterworth shelving. But but I might further go into the elliptic range if I'm ready to allow ripples in the shelving bands. And then I can make it even more steep. And the thing is that both filters are connected at this Butterworth position. I can start from Butterworth and go into the elliptic range. In a trivial way, using the low-pass to band-pass transformation, I can build a band shelving filter with a similar functionality. So I'm having a slope control, again, in the wide range, this time going from 2-pole to 8-pole. And I could go into the elliptic range. And I can also vary the bandwidth this time because it's just a parameter of the low-pass to band-pass transformation, independent. So I'm having some extra features which I could implement in equalizers, basically. And I would like for a short moment to return to this high shelving filter because I think it has very beautiful pole zero plot, which I would like to demonstrate here. So I'm enabling now the pole zero display. It's analog pole zero plot. So S-plane, you're having imaginary axis approximately here, and this is negative real axis. And you start just with 1, 0, and 1 pole, which are at mutually reciprocal positions and controlled by the shelving gain. And all other poles and zeros are canceling each other. And if I increase the slope a bit, you can see another pair appearing here. So they were canceling each other. Now they are not anymore. And if I just continuously increase the slope, we're getting a beautiful kaleidoscopic picture of these poles and zeros. I think it's really beautiful. So I built this setup specifically just to show you this picture. And I could go into the elliptic range. So one final demonstration. This one is more like a teaser, because I'm not going to explain which filter this is. This is from a more practically looking part of the new material. Again, it's actually part of the research which was done exactly in the way how I explained to you I want people to think in DSP. So in terms of analog block diagrams, I was basically researching some ways to build the filters, thinking in terms of analog block diagrams, and came ultimately across a filter, which I'm now going to demonstrate to you. There's actually a YouTube talk, like a talk of YouTube on YouTube, where I explain all details about this filter. Maybe some of you have seen it. For others, it's going to be just a teaser. You might want to read the book or show the talk, or see the talk. So this is going to be a completely static setup, a sawtooth going through the filter, no modulations whatsoever. It might sound as if there is audio rate FM going on. It's not. I'm only going to be turning the cutoff knob. So this is the basic sound of the filter. So that's it with the show-off. I hope you enjoyed the demos. OK, this illustration to what I already shown. Basically, to conclude the talk, I wanted to find some further reading. Unfortunately, so far, I'm not aware of many materials following the same paradigm. So for one, there is a book by Will Perkle. It's a printed one, actually. I haven't read it, seen some preview pages. And it's not only dealing with the filters, but in the part which is dealing with the filters, it's following the same approach. So you might want to check this book out. And I would like to mention a very short text available by internet by Stefan Schön. I hope I pronounced the name right. For me, the most interesting part of this text is that there is an intuitive introduction into the idea of integrators, which are the key concept behind the topology-preserving transform and basically material of this book. And people who are not deeply familiar with calculus might find this idea kind of, again, daunting. And this is a very nice intuitive introduction to this thing. Also, you might want to check it out. That has been it. Thank you for listening. I hope you enjoyed the demos. Any questions?
Let's hear it for Vadim. Just lead off very quickly with one question. Where do we get your book?
As I said, it's freely available from Nature Instruments website. It's actually in the reactor part of the website. You need to browse in there. So easiest is to just Google and click on the link in the KVR audio forum, because there is a dedicated thread in the KVR audio. And in the first message of this thread, there is an updated link always to the latest revision of the book, which is currently 2.1.0.
Fantastic. You have before you a font of filter wisdom. Let's hear some questions. Great.
Uh-oh.
Thanks for the talk. It was very enjoyable. I'm a musician and a computer programmer, not a DSP person, but I was wondering what your filter would sound like if you modulated it at audio rates. You did that for the other stuff, but you didn't do it for your own filters. Does it work, and what does it sound like?
You mean the last one which I showed? Or just generally all these filters?
The four-pole second kind Butterworth filter, I was wondering what that would sound like if you modulated with an LFO at audio rates.
Well, unfortunately, I can't patch it up here quickly enough on stage until the end of the talk. But if you're interested, maybe we can try it together after the talk. If Florian would still lend us his laptop, we can try it out.
Okay, thank you.
Anyone else?
Yeah, what's the sort of computational overhead of these filters versus the more classical, naive filters? You know, do they cost twice as much to calculate or something? What's the trade-off?
I think twice as much is probably the upper limit. So for one pole you can do in 4 operations, and I think as good as you get with classical filters is 3, maybe, I'm not sure. For the state variable filter, I think you get 10 operations for all, multiply-add operations, I mean, for all 3 modes. And if you want just a bandpass, I think you can get it with 8. In comparison, I'm not sure, maybe you need 5 or 6 with direct form 2, which again, like I illustrated, that it can have quantization issues, and besides just modulation issues. If you're comparing it to Euler-like schemes, coefficient update is, of course, more expensive because you normally compute tangent as part of pre-warping, which naive filters or Euler filters don't do. But that's the same thing which you get from classical DSP forms. You also need to pre-warp there. So, yeah, that's the comparison. For complicated filter structures, I think it can get more complicated. For example, I once, just for fun of it, took Pro53 filter, because sometimes it makes very nice sounds, and I wanted to convert it to ZDF filter. And it kind of worked, but there was significant overhead, although I didn't really optimize it out. It was just something very quickly patched up. So sometimes it can get expensive. Also, the thing about topology-preserving transform is that it gives you kind of standard routine for solving the linear equations which emerge there. You don't solve the abstract equation system, but they kind of are structured by your feedback nesting. but maybe it's not always the most efficient form. I can't tell you. So generally, they are a bit more expensive, yes, but like 2 times is probably the top. Like, you don't even get 2 times more expensive.
Any more questions?
Hi, thank you for the talk. I was wondering, have you tried other topology-preserving integrators? There are a lot of different methods who are also topology-preserving, and do they affect sound, or have you worked on that or tried that?
Are we talking of bilinear transformed integrators or about a wider range?
No, the integrators. You use topology-preserving integrators for your for the integration. The trapezoidal is just one of many integrators you could use. Have you tried other ones?
You mean like other integration methods? Because there are at least 4 different trapezoidal integrations which you can use.
Yeah, no.
But you don't mean trapezoidal. You mean just other integration schemes.
Other the standard Euler, for instance, or other. I think in ODE computation are known as symplectic methods. And there are a lot of methods which are computationally more expensive, but have you experience with them? Or
no, I haven't. I have tried, well, not tried, but kind of in my mind thought one can use forward and backward difference Euler directly there, but what would be the point? It's the same as applying forward and backward difference, and you have, again, large distortion in your frequency response. At least, like, I haven't found usage case for this. Maybe there are, but like I'm not aware of this. Mm-hmm. And for other integration schemes, I didn't try them. And also, I think we're limited in the choice of integration schemes. The integrators must be causal. Otherwise, we can't resolve zero delay feedback. Mm. Yeah, I can't answer your question. I haven't tried other schemes.
OK, thank you.
But you can try them, of course. Yeah.
After reading your book.
Well, in that sense, as I mentioned, topology-preserving transform is basically just expression of symbolic integration. So in principle, it's the same, just visually, just done visually, which I think is more intuitive. And you also kind of get different insights from visual diagrams, like especially, for example, when you get into the limits of trapezoidal integration, it's like very intuitive in a diagram form because you get kind of instantaneously unstable feedback at this point, and then like you can think in these terms and also even think like, how can I treat it? It gives you some other insights, but otherwise it's equivalent.
Maybe one last question. Anyone? Let's thank Vadim for his excellent talk.